Hi everybody. As a follow-up to the project we did on the little millivolt meter here, today in part 3 I'm going to cover off some changes I've made to the input protection circuit, and in addition to that I've also added two new features to this project. The first one is the ability to store the calibration setting in some non-volatile memory, which means that you don't have to recalibrate it every time you switch the unit on. And secondly, I'll be adding a button to give the user the ability to set their own number of decimal places on the display, so you can select from 0 up to 6. So I think the first thing we'll do, we'll have a look at the changes that I've made to the input protection circuit.
Right, well here we see the input circuit of our little millivolt meter project, and if you recall, initially we had a protection Zener diode here, a 5.1 volt Zener, protecting the input of the buffer op amp from the input voltage rising greater than 5.1 volts. The Zener diode also had some protection if the voltage went negative. It would then act as a normal diode and clamp it down to ground. But I did get a lot of comments about using a Zener diode in this position, and that was mainly due to the possible noise effects that could be caused by a Zener diode. So what I've done here is I've replaced the Zener diode with two Schottky diodes. Now the benefit of using Schottky diodes is that unlike a normal silicon diode, their forward voltage drop is much less. You will probably know that the forward voltage drop of a normal silicon diode is around 0.6 to 0.7 of a volt, whereas the Schottky diodes have a forward voltage drop of only between 0.15 and 0.45 of a volt, so much less than a conventional silicon diode. In addition to that, the switching speed of the Schottky diodes is far superior, much faster than a normal silicon diode. So for a protection circuit, you can clearly see what the benefits would be for that. So if the input voltage coming to the positive input of the op-amp buffer here starts to go negative for any reason, then this Schottky diode conducts and clamps it down to ground. If it goes positive greater than the supply of 5 volts, then the top Schottky diode here will conduct and clamp the input to around 5 volts, preventing any damage to the input circuit here. And as I said, the speed at which that will happen is relatively fast, and so the protection is much greater than we would have had before with a conventional Zener diode, or even using conventional silicon diodes in this position here. Now, the other comments I had with regard to the input circuit of this project was the type of op-amp I was using. I selected the OP777 op-amp because it operates off a single 5 volt supply quite happily, and it has a very low offset voltage, so if you use it as a buffer you get very small errors, if any, with regard to the voltage that's fed out to the ADC. However, having said that, I have had a look at other possibilities of replacing this with another type of op-amp, and I think what I might do is cover off that in part 4 of the project. We can have a look at different op-amps in this position and see what difference it would make. But I must admit, I do find that the op-amp that we've originally chosen does work quite well, and in any event, if you're using this as a millivolt meter, it is quite accurate. It's only when you get into the microvolt range you might find that on the very lowest level of the microvolts you might not be able to get right down to 0. But that is, you're talking there of probably a few, 10 or so microvolts, which is extremely low. So for the purpose of our project, I think what we have at the moment is quite suitable. So I'm going to leave that there today with what we have, and add the new protection circuit in here. And I'll show you the board shortly and see how we've installed those diodes on the existing PCB.
Here we see the part of the printed circuit board where originally, I'll just point out, originally the Zener diode was positioned between those 2 points there, which I've now removed, and I'm going to replace that with a Schottky diode, the first of the 2 Schottky diodes, remembering that the cathode of the Schottky diode wants to go to the right, that point there. And then we need to take another shocky diode from that point towards plus 5 volts, and I'll show you how I did that in a moment. Right, the two shocky diodes that we'll be using for this purpose, I've got two small general purpose shocky diodes. I'm using BAT85, but you can use any sort of general purpose shocky diode for this particular purpose. Well, let me just install these shocky diodes on the board and you'll see how I've positioned them. Well, there you can see how I've positioned the two diodes, the first one there is obviously going in the same holes as we had the Zener diode. The second one is going in one of the holes there, joins up with the first shocky diode, and then I've just drilled another little hole there next to that tantalum capacitor, which allows me to then solder it to the plus 5 volts on the other side of the PCB. So that's the input protection now installed. The first new feature we're going to add to the millivolt meter today is to store the calibration setting in some non-volatile memory. Now you recall previously that when we calibrated this little millivolt meter, we did that when we switched on by pressing the calibration button. But unfortunately, if you switch the unit off and then on again, it doesn't remember that calibration setting, so you have to go through the whole process yet again. So I thought it'd be a good idea if we could store that calibration factor in some non-volatile memory on the Arduino and then recall it next time we switch on. So this resolves the problem of having to calibrate the meter every time you turn the meter on. Now it just so happens that the Arduino does have 512 bytes of EEPROM, that's electrically alterable programmable read-only memory, and we're going to use some of that today to store our calibration factor, and then we can use that in the program to automatically calibrate the meter every time we switch the meter on. Now, as I say, the Arduino only has 512 bytes of this non-volatile memory that we can use, and each memory location can only store 8 bits. Now, our calibration factor is actually a 32-bit number, 32-bit long number. So what we're going to have to do is we're going to have to break down that 32-bit number into 4 groups of 8 bits. And then we can store those 4 groups of 8 into 4 memory locations in the non-volatile memory in the Arduino. And then when we want to recall them, we have to add them together again to use them in our program to automatically calibrate the meter every time the meter is switched on. So let's have a look at the additional software routines that I've put together to actually carry out this particular task. Right, well, the first routine that we're going to use to store our calibration factor, which is a 32-bit long number, and remember we've got to store it in 8 bits at a time into 4 memory locations, and we're using a command, the EEPROM command. It's the write command, which writes a long number, and to do that we're setting the address, the first memory address location. In our case that'll be a 0, and then we're taking the value, which is the long 32-bit calibration factor. And what this routine is doing is simply then splitting the 32-bit number into 4 groups of 8 bits. So the first thing it does here, it sets a variable called byte 4 equal to the value, which is our 32-bit number, and if we AND that with FF, effectively what we do is we extract from the 32-bit number the first 8 bits, and that's stored in a variable called byte 4. So they're the least significant, or the least significant byte. The next thing we do is we have another variable called byte 3, and here we store the value again, but this time we shift it 8 places to the right, so the first 8 bits drop off. So we're now looking at the next 8 bits. If we AND that with FF again, we extract the next 8 bits, and that's stored in the variable byte 3. We do the same again for the variable byte 2. This time we take the 32-bit variable and we shift it now 16 places to the right, so the first 16 bits drop off, We then AND the result again with FF, so we extract the next 8 bits, and that's stored in variable byte 2. And finally, byte 1 variable, we take the value once again, we shift it 24 places to the right, so the first 3 bytes have dropped off, and then we AND the remainder with FF, and in that way we extract the last 8 bits of our 32-bit number, and that's stored in memory in variable byte 1. That's the most significant bit. Now the next thing we do, we have to store those 4 8-bit variables now in 4 memory locations in the EEPROM. And to do that we use the command EEPROM write. So we write in the address, which is the, in our case it will be the location 0, the first location, and we store byte 4. We then use the same command again, we increment the address by 1, so in the next address location we store byte 3. We then do the same again for byte 2, but this time we've moved the address to the address location plus 2. And finally we increase the address location to address plus 3 and store the variable byte 1 in that location. So we now have a 32-bit number split into 4 groups of 8 and stored in 4 separate memory locations in the non-volatile memory of the Arduino. And that's ready now for us to extract later. Right, well the next part of our subroutine is a little routine here to read back the calibration that's stored in the non-volatile memory, and so we have to then read it and then reconstitute it as a 32-bit long value. And to do that, this little routine here, which is called long EEPROM read long, and that is the address, the start address again. And this time we want these variables to be set as a long variable rather than a byte. So we've said that the first one, called long 4, is equal to reading what's in the memory location of the first address, which is 0. We then read the next address, and that so the next variable is long 3 is equal to what's in address plus 1, and long 2 is equal to what's in address plus 2, and finally long 1 is equal to what's in address plus 3. So we've extracted those 4 bytes from memory, and they're now in these variables long 4 through to long 1. And before we return back to our main program, we have to add those together again to reconstitute the 32-bit number. And that's what this is doing here. It's simply adding the first variable 4 with the next variable 3, but shifting it 8 places to the left. We then add variable 2, which is shifted 16 places to the left, and we finally add variable 1, which is shifted 24 places to the left. So we're now just adding those groups of 8 bytes together again, and then returning back to the main program, and our value, it'll be equal to our 32-bit number. So we can then use that to automatically calibrate the meter. Now you'll recall that when we wanted to calibrate the meter, we shorted the input and pressed the calibration button, and then that called the subroutine for calibration. And what we're seeing here is the last few lines of that calibration subroutine we had on the initial software. And the only thing we've done is we've added one more line at the bottom of that routine. So immediately after the command LCD print brackets, inverted commas, millivolt meter, inverted brackets, and then semicolon there. So after that command, we simply add in this new command here I've highlighted in yellow, which is calling the write command to write the calibration factor into the non-volatile memory. So that is taking the address, which we'll set at the beginning of our program to address 0, the start address, and it takes the calibration factor here that we've got, and it stores it in the non-volatile memory. So that's what that command does. So it's just adding one more line to the end of the calibration subroutine. And the final thing we need to do for the calibration is in our setup routine in our software, after we had the word printed there, hobby electronic, in between that and the delay 3000 there, we are going to add a few more lines in our setup procedure. And so what we're adding is we're adding another delay there to give us delay from the intro screen. We're then clearing the LCD, we're resetting the cursor back to the start first row on the left. We then set in the variable cal to equal what's in our non-volatile memory. So that's reading the EEPROM with you give it the first start address, which is 0, and then that reads the calibration from memory. We then print what we read from memory, but before we do that, on the top line we print the words EEPROM cal level. We then move to the second line of the LCD and we print the actual calibration factor that we've read from memory, so you can see what the calibration factor is. We give another short delay and then we carry on with the setup routine as before. So all we're doing here is we're reading the calibration and we're briefly showing it on the LCD to show you that it's done the calibration and what the calibration is. Now, in addition to the other changes that I made in the software, we need to make a few alterations to the start of our program to take account of the fact that we're now going to use the routines to store the calibration into memory. So I'll just point them out at the start of the program. There's 3 changes here relating to that. The first is I've added another include there, include EEPROM, and that allows us to use the library of commands for the EEPROM, so we can write and store to that non-volatile memory. And in addition to that, I've changed the variable which we call cal from a float variable to a long variable. And then the final thing relating to the storage of the calibration setting at the bottom here, I've added another variable called the long address variable, set it to 0 as that is the start location of the EEPROM memory we want to use. Here we have the additional circuit that we need to give us the extra feature to increment the number of decimal places on the display, and we're simply using the digital pin D9 on the Arduino, which at the moment they had a little sort of test pin there. We're going to utilise that, and we're connecting a 10k pull-up resistor from that pin to the plus 5 volt supply, and we're taking D9 down through a little tactile push button to ground to give us the button required to increment the number of decimal places on the display. Now, to give a little bit of protection against any debounce on that button, I've added a 0.01 microfarad capacitor, but we may find that we have to improve that part of the circuit if we have any debounce on that button, and it could be that we need to add something like a Schmidt trigger, but for the time being, let's keep the circuit simple and see how we go. Now, I will mention that it is important that if you download and use the new software version for this project, you do need to add this additional circuitry, particularly the resistor, the 10k resistor pulling D9 up to plus 5 volts, because if you don't have that resistor in place and you try using the new software version, you may find the software hangs. So just a little word of caution there. So that's all there is to the additional circuitry, quite simple to put together on the board. And also the button itself, you can either add that onto the board or you can have some flying leads and have the button away from the board, whatever your preferences are. I'll also point out the small changes I made to provide the adjustment on the decimal places with an additional button there. You can see I've put a little tactile button there which is going from digital pin 9 of the Arduino. We had a pin there, remember, and the other end of the tactile button I've got it going to ground. And then we've added another resistor there, a 10k resistor, which is going from digital pin 9 to plus 5 volts. And that particular resistor, I just drilled a couple of small holes there, one there and one near digital pin 9 of the Arduino, and then just soldered the 10k resistor in. Now on the reverse side of the board, across the tactile button there, I've put a 0.01 microfarad capacitor. Just show you that. And all I've done there is, you'll see, I've just soldered that small capacitor, and it's just going across the tactile button to give us a bit of debalance protection. Right, well here we have the short subroutine we're including now to increment the number of decimal places on the display. This is called every time we press the new button we're installing now to increment that display. Now basically when this subroutine is called, all it's simply doing is adding 1 to the decimal place factor. Now if you recall, in the main program the variable D indicated the number of decimal places which were printed on the display, and what we're going to do is add an additional factor to that to increment it by 1, and the incremental factor is variable DA. So every time we call this loop, it increments DA by 1, and then in the main program it adds that to the D variable and shifts the decimal place on the display. Now it then returns back to the main program once you've called this subroutine, unless you have a situation where the number of decimal places on the display exceeds 6, in which case you want it to revert back to 0 again, so it cycles round. And that's the reason for the if statement in this subroutine. It's checking to see if the D variable is greater than 5. If that's the case, then the decimal places on the display has exceeded 6, and then it resets everything to 0. So you can see here it resets the DA to 0, that's the incremental variable here from the subroutine, and it also changes the decimal places for microvolts, millivolts or volts all back to 0, so it's a starting position once more, and then reverts back to the program. But if it goes into this sort of routine, then it also cleans up the display on the second line of the display, because you may have some erroneous characters there, and that's the reason for the LCD cursor moving to the second line 6 places in, and then printing 8 spaces to clear that part of the display, and then returning to the main program. So basically that's the simple subroutine that we're going to use to increment the decimal places. Right, well in order to use this new feature of incrementing the number of decimal places on the display, I've added a few lines of code here in the loop part of the software, and that comes immediately after the lines that appertain to the calibration button. So you can see here in highlighted in yellow are the extra lines that we've added to detect when the increment the decimal place button has been pressed, and in this case we're looking to see when it's taken low, so we're taking it down to ground. Once it detects that button is pressed, it then simply goes to the subroutine that increments the decimal place by 1. It then returns. We have a short delay there of 500 milliseconds, and then it continues with the remainder of the program. But I've also added here on the second line of the display, the far right hand side of that, a digit that indicates the number of decimal places. So where we've got this LCD cursor 15.1 and LCD print D, that simply is printing on the far right of the bottom line of the display the number of decimal places. Now this is a little feature that if you wanted you could remove, so if you didn't want that to be displayed you can simply remove these 2 lines here. But we'll demonstrate that when we have a look at the actual unit. Now towards the bottom of the main loop of the software I've also had to add one more line there, and that's coming at that point there immediately after we've had the V and the DV indications there, and we've just added one line there which is D equals D plus DA, and simply all we're doing there is we're adding the additional increment value to the existing decimal place position, and then it's printing on the screen the voltage to the required number of decimal places. So just one extra line of code there. Right, well finally we also had to add a few lines at the beginning of the software code here for the decimal place adjustment, and that is we have the constant integer here. That's setting the button, the push button that we're using for digital pin 9 in this case, which is quite convenient because we had that pin on the original project, which I said was for future upgrades. It was already there. And then we also have a couple more integers here. We have an integer there, decimal places equal to 0. And finally at the bottom here we have the integer DA, that's the decimal place adjustment in the subroutine. That's initially set at 0. So it's those 3 lines that have been added to the initial part of the program. Right, well I've got the new software uploaded into the Arduino now, but I've got power via the USB port disconnected for the moment. And I have a multimeter monitoring the 5-volt rail on the board, so we'll have a look at that as well. So I want you to have a look at first of all the display when we connect the USB power back to the device here, and have a look at after the startup sequence of Scullcom Hobby Electronic. You'll see a screen showing you what's stored in the non-volatile memory. And it should be 0 because we haven't put anything in yet. So let me just now restore the power by plugging in the USB lead. So I've connected the power, and we should get the startup sequence there, the welcome screen, and then there you can see we've got 0 stored in the EEPROM because we haven't done any calibration yet, and then it goes to the normal display for the meter. It's currently showing 44.61 millivolts. We've got nothing going in. The leads are open at the moment, so it's just random noise going in. And you'll see on the right hand side of the display we've got a 2, which is indicating the number of decimal places set. Now by default, when we switch on, under normal conditions, the millivolts will always be 2 decimal places. Microvolts will be no decimal places, and if it's in the voltage range of readings, it will give you 6 decimal places. But as I'll show you a little bit later, we have an ability to override that and adjust the number of decimal places by using this button that we've installed. Now, before I look at that, now I want to look at the 5-volt rail for this module at the moment. You can see the meters monitoring there the 5-volt rail. It's only showing 4.7 volts, and the reason behind that is that on the Arduino module here, the USB power is isolated via a Schottky diode, and the Schottky diode used has a forward voltage drop of 0.3 of a volt. So you can see that we've only got 4.7 volts on the 5-volt rail on the board, which is not ideal for our project, as we would need 5 volts really for the analog to digital converter IC. So when you're using the module correctly, you do need a 9-volt battery or a 9-volt source powering the module, so you can get 5 volts on the 5-volt rail. So what I'm going to do now is I'm going to just connect the 9-volt battery I have here, and you should see on the meter there that the voltage level should go up to 5 volts. There, the battery is now connected. We've got 5 volts on the power on the board now, which is ideal for the circuitry there. What we can do now, if you wish, we can unplug the USB lead if you wanted to. So I'll just disconnect the USB lead from the board. So it's now being powered by the battery, and the first thing we're going to do is I'm just going to do a calibration, and to do that we're going to short the 2 input leads together. So I've shorted the input, and now when I press the calibration button, not only will it show us the calibration factor, at the same time it will store that into the non-volatile memory in the Arduino. So let me press the calibration button. So it's calibrating, gives the calibration factor there 17163, and it's stored that calibration factor now in the EEPROM on the Arduino. So even after the power has been removed, next time it's restored, it will remember that and will use that for its automatic calibration purposes. So now with the lead shot on the input, we're reading a few tens of microvolts, and you'll notice that we've got no decimal places there on that. So the next thing we're going to do is I'm going to disconnect the power to the unit and then reinstate the power, and I just want you to monitor the display this time, and you should see in the startup sequence the calibration factor that's stored in the EEPROM. So let me just do that. So disconnect the power and reconnect the power. Although you can see the 17163 is stored in EEPROM, and it uses that to automatically calibrate the meter. Now, just so we can test that, I'm going to check the 4.096 volts on this pin here. And there we are. There's the 4.096 volts is reading 4.0958 of a volt, which is close enough there. And you'll notice we've got 6 decimal places, and the indication there is telling us that we've got 6 places. Now, that digit on the right hand side, if you didn't want that to be shown on the display, you can simply remove 2 lines of code in the software to remove that altogether if you wish. Now the next thing I want to do is show you the effect of the button here. I'm just going to disconnect the voltage for the moment, so there's nothing on the input. So it should be reading some noise or something in millivolts, and you can see that when we're on the millivolt range it's reading to 2 decimal places, 4.67 or so millivolts. Now we've got the extra button here now which we can use to increment the number of decimal places. I have a delay on that, so the clicking sequence is you press it and hold it for a second and let go, and it should increment one at a time. I'm not sure how effective it's going to be at the moment because I've only got a 0.01 microfarad capacitor across it to prevent any sort of bounce on the button. But let's just see how it works. So let me press the button. Pressed it once and we've gone to 3 decimal places. Press it again. We've gone to 4 decimal places. Again, 5 decimal places. 6 decimal places, and then next time we press it should go back to 0. Let's just 0, so we've got no decimal. Well, I hope you found part 3 of this project of interest, where we've made a little change to the protection circuit on the input and added 2 new features, the calibration storage and the ability to change the number of decimal places. I must say that the little button we added to change the decimal places can be a little bit temperamental at times, probably because of key bounce, and we may need to improve that by adding, say, a Schmidt trigger or something. But I'll leave that to another episode. And also we'll have a look in future, I think, at the op-amp on the input and see whether other devices may prove to be better, and look at possibly adding things like additional voltage ranges on the input circuitry. The other interesting point was the fact that we could use the non-volatile memory in the Arduino. I know there's not a great deal, but there could be enough there to store some voltages and to recall them. So I may consider that as another addition for later, where we can store voltages and recall them later, or do some mathematical calculations on voltage that we read. But for now I'm going to leave it there. I'll put a link down below with the new software version which you can download and upload onto your project. In the meantime, if you found this of interest, please give me a thumbs up, and I'll see you all again soon next time. Bye for now.